All right, guys. I'm gonna pick up where I left off from the last video. Last video, I did questions 1 through 17. Questions 18, 19, and 20 should seem familiar to you because we did these actually during the practice problems in class for Half-Life. So I'm gonna start there anyways, so you can watch us do it again. We can do it all together. Okay, so let's see if I can get this pen to work. All right. Yes, okay. Works. All right. Bear with me, guys. Okie dokes. So, if 3 grams of strontium-90 in a rock sample remained in 1989, approximately how many grams of strontium were present in the original rock sample in 1933? So, one thing that we're going to want to do is let's just go and look at the half-life for strontium-90, and we can see here that it is 29.1 years. So basically this means every 29.1 years, strontium-90 will decay in half. So I'm just gonna write up here, our half-life is 29.1 years. So let's figure out how long or what the time elapsed is. So it's 1989 minus 1933. And this means that 56 years have gone by. Okay. And if we think about 56 years, that's the time elapsed. And I know each half-life is 29.1 years. So how many half-life periods am I going to go through? And that would be 2 half-life periods. So this thing decayed 2 times. Now this problem gives us the ending amount that we have. So we ended up with 3, but this thing went through 2 half-lives. So you're really working backwards. So what would this have been before it decayed? Well, it would have been double. It would have been 6. And what would this have been? It would have also been double. So it would have been 12. So 12 grams is the original amount that we would have started with. So our answer should be choice D. All right, let's get rid of all this. All right, number 19. Okay, so we have 8 grams of a sample of cobalt-60 existed in 1990. Again, you would go to table N, look up the half-life. For cobalt-60, it is 5.271 years. Again, I got that from table N. So in which year will the remaining amount of cobalt-60 in the sample be 0.50 grams? So first we need to figure out how many half-life periods are actually happening. So we start from 8, then we can go to 4, then this divides into 2. I'm just going to continue this here. This goes to 1, and then this goes to 0.5. I count my arrows, 1, 2, 3, and 4. So we went through 4 half-life periods, okay? And each half-life period is a little over 5 years. So in order to get how many years have passed in total, I would multiply these, and I get about 21 years. And they want to know what year would I end up with only half a gram. So I started in 1990, but then 21 years later is when I'll have only 0.5 grams left. So you add these together and you should get the year 2011. So that should be our final answer. All right, number 20. A bit of an easier one. So if 80 milligrams of a radioactive element decays to 10 milligrams in 30 minutes, what is the half-life in minutes? So we need to know how many half-life periods happen. So we need to figure out how to get from 80 to 10. How many times does this thing have to decay? We go from 80 to 40 to 20 and then to 10. So I had 1, 2, 3 half-lives. Okay. Again, you can use the formula, but in 30 minutes, basically, 3 half-life periods occurred. So that means that each half-life period lasted for 10 minutes. This means that the half-life is 10 minutes long. So this should be A. All right, 21. we didn't do this one, and we didn't do the next one either. So if a radioactive substance has a half-life of 9 days, what fraction of its original mass would remain after 27 days? So again, you can plug everything into your formula. So what we want to know is how many half-life periods have happened. So each half-life is 9 days and 27 days have passed. 9 goes into 27 3 times. That's 27 divided by 9. So this thing decays 3 times. Okay. Now they don't give us a starting mass or anything like that. Okay. These fractions will apply for any mass that you start with. So let's just pretend that we start off with 1 gram of a substance. Okay. If we start off with 1 gram and we go through 1 half-life, we're going to end up with 0.5, which is really just half, 1/2. Okay. Then if we decay again, we will end up with 0.25. This is a quarter. And again, this would work for any amount that you start off with or end with. It's just easier if you start with 1. Now for a third half-life, we are going to end up with 0.125 grams. And this is 1/8 of what we originally started with. If you take this 0.125 and multiply by 8, you will get 1. So this is 1/8 of what we started with. So our answer should be 1/8. And again, these fractions apply for any isotope at all. So any isotope after 3 half-life periods, you'll have 1/8 of what you started with. If you went through 4 half-life periods, you'd end up with 1/16, so on and so forth. The next one. So if a radioactive, nope, I am rereading the same thing. Okay. I feel like this might be out of order. Let me scroll up for a second. My paper looks very different. But I'm just going to continue. So if your questions are out of order on the paper, you're honestly just going to have to go back and I guess find the question that matches up with the one that I'm doing. So sorry about that, but that's what we're dealing with. So we'll just continue. Anyways, the next one, the half-life of a radioactive substance is 2.5 minutes. What fraction of the original radioactive substance remains after 10 minutes? So again, we need to figure out how many half-life periods are we going through. So again, 10 minutes have passed, and each half-life is 2.5 minutes long. This means that we have gone through 4 half-life periods. So again, this is similar to what we did before. So the last question, we start off with 1 gram. They don't tell us how much we start off with, and it really doesn't matter. Let's say we start off with 1 gram, go through 1 half-life, we've got 0.5, another 0.25, another 0.125, and another, we would have 0.625. This is 1/2 of what we started with. This is a quarter, 1/4. This is 1/8. And right here, this is 1/16 of what we originally started with. So our answer for this one should be choice D. Alrighty. Next one. At least on my paper, 23, what total mass of a 16-gram sample of cobalt-60 will remain unchanged after 15.9 years? Again, we also did this one in class. This is one of the ones on our posters. So we've got 16 grams. So we start off with 16 grams. I'm just going to put this up here, and this is going to decay into some amount. Cobalt-60, again, has a half-life of 5.271 years. Now they're telling us that 15.9 years have passed. So it's really going to be 15.9 divided by the half-life. And this gives us 3 half-life periods. So this thing has decayed 3 times. I think this is 3. Yeah, 3 half-life periods. Okay, so if it goes through 3 half-life periods, we're going to go once, that's 8, another time, that is 4, and one last time, that is 2. So we will end up with 2 grams of our cobalt-60. The rest has decayed into some other element. Okay. Next one, 24. Atoms of one element are converted to atoms of another element through, and this is just a definition, this is what we've been talking about for the entire unit. This is simply transmutation. Transmutation, again, is when you take one element and you turn it into another through some sort of decay. Alpha decay, beta decay, positron emission. We also have gamma decay or gamma radiation, but we don't actually end up changing the identity of our element. So I wouldn't necessarily consider it to be a transmutation because we don't actually change the element. This one I'm going to zoom in for so we can see the graph. All right. So this one, they're plotting a graph of this isotope's half-life. So they're showing us the isotope decaying. You can see that we start off with 10 grams, and after many decades, we are tapering off, and all of this isotope is decaying again into some other element. And remember that we will never actually reach 0. So they are asking to read this graph basically and figure out what the half-life is. So let's start off with 10. So we start off this graph at 10 grams. Okay, now after one half-life, we would have 5 grams. So I want to find where 5 grams is on here. 5 grams is right here in the middle mark in between 6 and 4 grams. And right here, I can see that this ends up somewhere pretty much right in the middle between 20 and 40. This means that one half-life period is 30 years. Again, you can check this if you want. You can look at the next one. So if we're here at 5 grams at year 30, after another half-life, we will have 2.5 grams. Now, right here, the middle mark is 3. So 2.5 would be right here somewhere. So I will just bring this across and see where this hits pretty much. And this is somewhere over here. So it's pretty much at 60. And again, that's 30, year 30 to year 60. Again, that is 30 years. So our half-life for whatever isotope this is 30 years long. Again, it would take 30 years for this thing to be able to decay in half. So our answer is B. Okay. Next one. Which equation represents artificial transmutation? Now, 2 of these are very easy to kind of eliminate. Again, a transmutation means that you are ending up with a different element. We can see in choice A, we have hydrogen and oxygen on this side, and on the other side, we also have hydrogen and oxygen. They are just arranged in a different way. So this is not a transmutation. It's not a nuclear reaction at all. Same thing applies for B, same elements on both sides. Now the next one, we see uranium is going through, this is alpha decay. Alpha decay happens naturally. So uranium-238 will naturally decay into thorium-234. So this one doesn't count. Again, alpha decay, beta decay, and gamma are all natural types of radioactive change. Okay. The last one, we can see that aluminum is being basically bombarded. This is alpha bombardment. It's being bombarded purposefully with an alpha particle. Again, one of the key signs is that you will see 2 reactants on this. So you'll see two things on the reactant side. So you'll start off with 2 reactants, and that's a telltale sign that you have an artificial transmutation. And again, make sure that you actually have a transmutation. We can see clearly here we have aluminum and helium. And then on the other side, we end up with phosphorus. So definitely a transmutation. So this should be choice D. Alrighty. Number 27. Let's scroll down a little. Okay. Radioactive cobalt-60 is used in radiation therapy treatment, and it undergoes a beta decay. Again, I just said this, right? So again, alpha decay, beta decay, and gamma radiation, these are all natural processes. So this would be considered a natural transmutation. Another question similar to this, which equation represents a transmutation reaction? Again, transmutation means that you should have different elements on both sides. So number A, this is good for us to look at. This is something undergoing gamma radiation. So gamma radiation is basically when an element releases a ton of energy, and it does help to stabilize the element or the isotope, but it doesn't actually change its identity. Nothing actually happens to the atomic number. So even though this is nothing is happening, well, sorry, nothing is changing here. Okay, it is nuclear. It's a nuclear reaction because we have gamma radiation over here, but it's not a transmutation because we're not actually changing the element. So it's definitely not A. B, I can clearly see I go from carbon and we turn it into nitrogen through beta decay. So this is going to be our choice, but let's just look on the other side. Again, we can see here C, same thing that we saw in the other problem. We've got the same elements on both sides. We've got carbon, hydrogen, and oxygen here, and carbon, hydrogen, and oxygen on the product side as well. So it's not a C. That's not a transmutation at all. It's not even a nuclear reaction. D also is not a nuclear reaction. We have carbon and hydrogen, and then we also have carbon and hydrogen on the other side as well. So B would be our final answer. Okay. Just don't mind my babbling and my jumbling of my words. I am doing this at, yes, 9:20 at night. Okay. Alrighty. Next one is 29. Given the following reaction, which type of reaction is being represented? So we can see here that we have beryllium and it is being bombarded with hydrogen, or really this is a proton. So we have two reactants on the left side, so two things on the reactant side. So this is definitely not natural transmutation. Okay. This is also not considered fusion. Fusion, you'll typically see it is between hydrogen and hydrogen, making a helium. So it's not fusion. Fission is when you take a very, very heavy element and you break it down into other elements. So this is not fission. This is an example of artificial transmutation. All right. We can go to the next page. Next one. Which equation is an example of artificial transmutation? Okay. So again, artificial. So we want to be looking for the one that has two things on the reactant side. So I can see here, first one, this is alpha decay. Alpha decay, again, is natural. This one, I see two reactants here. This is alpha bombardment, taking aluminum 27 and bombarding with alpha particle and creating the unstable phosphorus isotope phosphorus 30. So this is going to be our choice. Okay, but let's just go through the other ones. Again, in C, we also see another type of natural transmutation. This is beta decay. This one doesn't count. And another alpha decay. Again, doesn't count. Alpha decay, beta decay, and gamma are all natural. All right. Which equation represents a spontaneous transmutation? This is a great question because instead of saying natural or artificial, they say spontaneous. When you see the word spontaneous, this means that something is doing it on its own. It's doing it naturally. It doesn't have to be forced. So what they're really saying is which equation represents a natural transmutation. So first off, make sure that you have an actual transmutation. Make sure you're looking at something nuclear. That's not gamma. For the first one, this is a chemical reaction. I've got calcium and I've got water. Calcium, hydrogen, oxygen on both sides. So this doesn't count. I don't change any elements. Same thing for choice B. Got potassium, chlorine, oxygen, and we've got the same elements on the other side. Here we see Pu 239 is absorbing two neutrons. So this, we've got two reactants. So this one is going to be artificial. This one is being forced. Calcium 37 is going through positron emission. So this one is going to be the spontaneous transmutation. All right. All right, 32. A particle accelerator is used to provide charged particles with sufficient. Now, the answer is kind of in the name. Okay. And again, if we're talking about nuclear chemistry, the word nuclear comes from the word nucleus. we are making changes to the nucleus of whatever element or isotope. So we want to avoid this electron cloud, electron cloud. Nuclear chemistry doesn't really make changes to the electrons. Not really, unless you're combining protons and electrons to make something else or whatever. But we're really making changes to the nucleus, and that is, again, how we get a nuclear change to occur. And if we want to accelerate something, again, that means we want to get it moving, and we want to get it moving fast. So the energy that is associated with movement is kinetic energy, not potential. So that should be choice A. Next one, which particles can be accelerated in an electric or magnetic field? The only types of things that can be accelerated or influenced by an electric or magnetic field are things with charges. So if we look at alpha and gamma, alpha has a charge of +2. Gamma has no charge, so it's not this. Only the alpha particle would be able to be accelerated. Beta particle, -1. Neutron, no charge, so it's not this one. Alpha particle has a charge of +2 and beta, -1. So both of them have charge, both would be able to be accelerated. So we're going to go with C, but let's just make sure that we can cross out D as well. Beta is, again, -1 and gamma is 0. So the gamma wouldn't be able to be accelerated. So yeah, final answer is C. All right, 34. Let me zoom out a little. All right, so we've got this diagram below representing a reaction, and I can see, I want to really pay attention to this arrow. Okay. So what is happening here is uranium-235 is being hit with a slow-moving neutron, and this should signal to you that we are going to go through a fission reaction. Okay, so this is fission. So the uranium is being broken up into Te and Zr, zirconium and tellurium, and we're also getting some neutrons out of the deal. And these neutrons will then go on to hit other atoms of uranium-235, and then we will produce our chain reaction. So which phrase best describes this type of reaction and the overall energy that occurs? So what we want to do here is look for one, we start off with uranium and we end up with 2 different elements. Okay, so we know that this is a nuclear change. So we can get rid of C and D. This is not a chemical change. We are not just rearranging atoms. We are completely changing the identities. So this is nuclear. And we know that fission and fusion are 2 reactions that produce immense amounts of energy. So we would always see energy on this side of the arrow. Energy is one of the products of a fission or fusion reaction. So energy is not being absorbed, but energy is being released. And if it's a fission or fusion reaction, a ton of energy is being released, especially in comparison to chemical reactions. Yolks, 35. When a uranium nucleus breaks up into fragments, pen again, which type of nuclear reaction occurs? Again, it means that we're breaking something up into fragments. Okay, redox, this is not it. Replacement, that's not it. We haven't gone through these yet. Okay, these are all chemical reactions. All right. When we break something up into fragments, right, we're taking something large and breaking it up into smaller pieces. This is the definition of fission. If we were taking 2 small atoms and combining them to make something bigger, that would be fusion, but that's not what we're talking about here. We are talking about fission. Again, the breaking up of something large into smaller pieces. All right. So given the nuclear equation below, this equation can best be described as, and this should be something that we recognize, if we see uranium being hit with a neutron, and then we see some other elements over here on this side, this is fission. Again, we have something heavy. Uranium-235 is a heavy isotope. It's heavy and it's being broken down into multiple other elements. This is the definition of fission. 37. An uncontrolled chain reaction takes place during the. So I'm actually going to scroll down for a sec. Right here, okay, this is a fission reaction. So this is something that could occur in a nuclear power plant. Now, when we have uranium-235, we hit it with a neutron and it will break up. So this is the kind of like the intermediate state. This is the uranium splitting up into two different elements, Te and Zr. Now, from this reaction, two neutrons also actually get released. These two neutrons go on to hit, let me get my pen, another uranium atom and another uranium atom. So this one hits this, sorry, this hits this, and then these will make more neutrons, and this process will continue on and on and on. Now, in a nuclear power plant, we can control this. However, if we do not control this, this is a problem. This would be known as the explosion of an atomic bomb. So this would be B, okay? If it was controlled, then the answer would have been A. But it is saying it is uncontrolled. So that would be an explosion. That would be an atomic bomb. All right. And again, uncontrolled chain reaction, this is also, it's got to be describing fission. So this is fission. And if we look at C, production of energy by the Earth's sun, that is done by fusion. And they're also talking about fusion in D, so that also doesn't work. All right. Next, 38, which substance has chemical properties similar to those of, sorry, lost my place. Where was I reading? Which substance has chemical properties similar to those of radioactive uranium-235? Now, we spoke about isotopes very briefly in terms of chemical versus physical properties. Now, their chemical properties are going to be the same. So isotopes of the same element, uranium-235, uranium-233, uranium-238, whatever isotope of uranium it is, they are all going to be chemically similar. So they will react with other things in a similar way. The only thing that is really going to be different about them is some of their physical properties. For example, if we look at uranium-235, its mass is 235 AMU. And uranium-233, its mass is 233. So obviously their mass is different. Mass is a physical property. If their mass is different, then compounds containing uranium-235 versus uranium-233 would also have different densities, okay? So the isotopes only differ in their physical property, not their chemical properties. So we would have wanted to go with choice C. Next one. Which balanced equation, and right now we don't know the word balanced yet, but we will know it in a few units from now. So which balanced equation represents a fusion reaction? Again, what we want to look for is two very lightweight nuclei combining to make a heavier atom. So in choice A, I should be able to, at this point, automatically recognize that this is fission. Taking uranium and breaking it up into krypton and barium, two smaller elements. This is fission, so not A. In B, I can see that I am taking two light nuclei. And again, typically you are going to see this with hydrogen. So you've got hydrogen 2 and hydrogen 3. And we're combining them to make helium, combining them to make one heavier element. So this is the one that we want to go with. All right. 40. Again, another problem like this, which balanced equation represents nuclear fusion. Again, we want to be looking for the things that are very light coming together to form one slightly heavier element. And we can see, again, this would be choice D. Again, you're really going to often see this with different versions of helium, the different isotopes of helium, hydrogen, coming together to form helium. That's usually the example that they will use, by the way, on the regent. 41. The fusion of hydrogen nuclei with the release of energy can be initiated by a fission reaction because the fission reaction provides A. So again, in our nuclear power plants, we use fission reactions. We use fission reactions because we haven't yet been able to replicate fusion reactions because the conditions that you need for fusion to happen are really, really intense. They require high temperature and very high pressure. Remember those values that I showed you? It was about 27 million degrees Fahrenheit in the center of the sun and about 260 billion atm of pressure. So very intense conditions, okay? You can get a fusion reaction to happen, okay? But you first have to get a fission reaction initiated, and then that can set off a fusion reaction. So in order for any fusion reaction to happen, it needs high temperature, high pressure. Let's move on to the next page. 42. Which pair of nuclei can undergo a fusion reaction? Again, this typically is going to happen between very light nuclei. So I want to look for the things with the smallest mass numbers, and I can just see right here that it would be choice D, hydrogen 2 and hydrogen 3. And those are typically the examples that you will see. Okay, we're given the following nuclear equation on 143. So we've got ES253, X, some particle, and then at the end we get a neutron and we get MD256. So we want to know which particle is represented, excuse me, by X. So using our knowledge of how nuclear equations work, we have to basically just fill in the blanks. Okay, so I see that on the product side, the total amount, the sum of the mass numbers is 257. So I know that the mass number up here has to be 257. I've already got 253 here. So the mass number for X would be 4. And down here, the total of our atomic numbers is 101. Over here, it's 99. I have to add 2 to 99 to get 101. So what has a mass of 4 and a charge of 2? That would be helium. So that would be what is being represented by particle X. All right, 44. Given the equation, again, another thing just like the last question, we have nitrogen 14 going through alpha bombardment. We end up with oxygen 17 and some other particle. So we need to figure out what the other particle is. Again, I can see here my mass numbers on the reactant side is 18. Over here it's 17, so this needs to be 1. Off the bat, I can eliminate A and D. The mass numbers don't match. And at the bottom, I can see that here on the reactant side, the atomic number is equal to 9. Over here, it's just 8. So this also needs a 1. So this is going to be hydrogen 1, or basically a proton. So choice C. All right, next one. According to the equation, the nucleus correctly represented by X is, so some element is going through alpha decay, and we need to figure out which one it is. So again, everything has to be balanced, just like a math equation. So on the top here, I see that my total needs to be 212, all right? And I also see that the bottom needs to be 84. So I'm just gonna write those out, 212 and 84. Now the really important number is the bottom one. It's the 84. Because that is our new atomic, or our starting atomic number. So what element is atomic number 84? That would be PO. So we would want to go with choice B. All right. 46. In the equation, another one, just like the last one. Again, we've got an alpha decay, and we're not given the reactant. So we need to figure out what the reactant is. I can see here on the product side, the top equals 226 plus 4. So the top should be 230. All right. And the bottom needs to add up to 90. So what element is element number 90? That would be TH, thorium. So thorium 230 would be our answer. So B. Another nuclear equation here, we got to figure out what is happening to fluorine 18. Now on the top here, I can see that this reactant side, total of 18. This reactant side already has 18. So that means that the mass number for particle X is going to be 0. Now the bottom, okay, the bottom on or the atomic number on the reactant side is 9. Over here it's 8. So this has to be a positive 1. So this is a positron. Again, you can also write it like this. You can write it either way, both are acceptable, but we would want to go with choice D. Okay. Um uh the paper. All right. Okay. I'm actually going to stop here. Get a drink of water, and I will come back. How many questions is this? 71, I think. So I'll try to see if I can do 48 to 71 in one go. Okay, so we will come back starting with question 48. Again, guys, I really hope that this is helpful, and also in the future, this will also be helpful for us to look back on when we want to start studying for our region in June. So I will be back and I will try to do questions 48 to 71 in one go. Thank you, guys.